Okay, I have to, it is, let's see, 2:37, and I need to get right to this because I already got the harassing email from Hadley about not sending the screencast early enough. So here goes. We're talking about collision theory. And before we can do that, we need to step back a little bit into something we've talked about already. And that is the concept of elementary steps. And we're going to talk a little bit more about these reaction mechanisms as they apply to why certain reactions will happen faster than others. So let me give you a mechanism, and this happens to be a three-step mechanism for the original, or I guess I shouldn't call it the original, but the overall reaction, which is what I'm going to put down right now. And there it is. One thing I want to point out to you is I want you to imagine a situation where this reaction takes place, where you would need to have four of these HBRs colliding with one O2 simultaneously. That's going to be a pretty low probability event to have those five things all coming together at exactly the right moment and in the exact space as well. And so as a result, we understand that that's not actually how this reaction takes place. It can be broken up into a set of elementary steps, as we've talked about before. So here are the three elementary steps that make up the reaction mechanism for this overall reaction. Here's the first part of the reaction mechanism, the first elementary step. Notice here, now all I need to do is make sure that one molecule of oxygen hits one molecule of the hydrogen bromide. So that's a much more likely event to have take place because it's only two things that happen that have to collide at the same time and place. Okay, here's the second elementary step. One thing I want to point out to you is notice that there is an intermediate product that's created. That's what this is called, because you don't see it hanging out in this overall reaction. This is an intermediate thing that will disappear pretty quickly. But the intermediate product becomes the reactant or a reactant in this second elementary step. And again, I only have two things having to collide, the HOOBr colliding with another of these HBRs to form two HOBRs. And then let's look at our third elementary step. And if you look, there's the third of the elementary steps. Now, don't be misled here. It's not that four things have to hit simultaneously. I had to put those, a coefficient of 2 with the HOBR. Let me point it out right here, and another one with the HBR, but this just has to be one HOBR connecting with one HBR, and when those two things come together and then another one of those two things come together, then you can create this product. And notice here that I have a whole bunch of reactants here. I have reactant here and another reactant here. I have, and those, what I talked about earlier, intermediate product being created, which becomes a reactant in the second elementary step, and then another intermediate product, which becomes a reactant in the next elementary step. And then finally, we can see we have here the products that are exactly the same as the products we have in our overall reaction. So this is the reaction mechanism. This is actually how it will take place. And the other thing that's important here is don't forget there's a rate determining step here. And in this case, it happens to be number 1. So this number 1 guy is relatively slow, whereas these two are fast. Okay. Now, the reason I bring this up is that I want us to focus in on this concept of collision and whether or not a collision is an effective collision or not. Because in order for the components to come together, they actually must make contact or collide with one another for the reaction to take place. So let's take a look at what makes a collision an effective collision here. What's vital to understand here is that there are some collisions that are effective and some of them that are ineffective, that will not lead to a reaction taking place. And the first part that a collision is dependent on, a successful collision is dependent upon, is the amount of energy involved. And this goes back to what we were talking about today in class. When you increase the kinetic energy, it makes the reaction rate go faster. And that's what, if you recall, the the K is very dependent on temperature, and temperature is a reflection of the kinetic energy of any particular reaction. So energy is key. And what do we need energy for? We need energy to break the bonds that hold the reactants together. So if we take a look at this HBr, right? HBr is held together with a covalent bond between the H and the Br. We need to bust that thing apart before we can begin the process of combining them into new things. All right, so take a moment to write that down. And obviously the type of energy that we're talking about is kinetic energy, the energy of movement. And if it's the energy of movement, then it's important that we focus in on two particular aspects of whatever the particle is that is involved. It could be an ion, or it could be an element, or it could be an entire compound if it doesn't break apart completely. So there are two things, and those two things are the velocity and the mass of the reactant. That should make some intuitive sense to you. If you're moving faster and you collide with something, you're going to be imparting more energy. And if you have more mass and you collide, then you're going to be imparting more energy as well. So there's nothing new to that. However, we do have this concept that we've touched on, ages ago, that I want to make sure I review with you. And that has to do with something called activation energy. So you need to have enough energy to overcome activation energy. So let's make a couple of graphs here to try to refresh your memory. I'm going to scooch over to here. Actually, I'm going to scooch up to this quadrant. So you may recall these activation or these energy diagrams that we looked at last term, I think it was. And we have energy on our y-axis, and this is high energy at this point, and we have low energy down here. And then across the x-axis we have time, which is essentially the progress of our reaction. And you may or may not recall that if we have the reactants up here, then we have the products at the end down here. And if the energy of your reactants is higher than the energy of products, that means somewhere along the way you've lost energy. And so if I just draw a dotted line until it extends out from our reactants to above our products, then I think you can all remember that this is the amount of energy that's released in this reaction. And if energy has been released, don't forget that we call this an exothermic reaction. Now, what's important here, though, is this little hill up here. This is the activation energy that we have. So I'm going to just bracket this thing in blue. From here to here is our activation energy, and we label that as E with a little fish pointing to the left there. Okay, activation energy. And that means that for our reactants to become products, they need to have enough energy so that they can overcome that little hill of energy. And in fact, there's a name for it when it reaches the pinnacle of this hill. So I'm just going to put a red asterisk up here. When we reach that point, and it's going to be essentially literally all downhill from here, we refer to that combination of particles that have come together as the activated complex. So I'm going to add that down here in the notes section. So it's important that we have we achieve the point of having an activated complex. So two of the particles come together with enough energy so that they can get up to that hill that we have up here and then have the reaction progress as it normally should. Okay? And then let's take a look at this from an endothermic standpoint. So we're going to do the same concept, but we're going to make it endothermic, something you probably do recall. Now we have a very similar situation going on here. I have my reactants down here, and then ultimately my products are at a higher energy level, which is the case for an endothermic reaction. So draw the dotted line to be in line with the products. We recall that this is the energy released, or actually the energy gained. Wait, where's my undo? energy gained, all right, between here and here. And yet we still have this fella right here. We still have to have this activation energy, the E fish, right? And we're going to have, yet again, the activated complex at the very top of this thing. So it needs to overshoot. You are going to take in energy, but you actually need to take in even a little bit more energy than that with our activation energy in order to finally reach the point where you have products here. So you're going to have activation energy whether you have an endothermic or an exothermic reaction. Did I write down exothermic? I sure did. I better write endothermic here. So in both cases, you need to have enough energy to overcome the activation energy and have the reaction take place, regardless of whether it's an exothermic reaction like you see there or an endothermic reaction as we see here. And in fact, what's a really key element here is that this activation energy can be either pretty big or it can be really small, and that's going to have a huge impact on the speed of your reaction. If something has a very small activation energy, then your reaction is going to happen faster. If something has a very large activation energy, it's going to happen more slowly. I think that makes some intuitive sense because it's going to require more energy in order for you to get over that hump and have your reaction take place. Okay, and then while energy is important in terms of making a collision effective, hold on a second, I got to check something. Okay, I just had to be sure that I actually wrote an A for energy, because now we have the second very important piece of what determines the effectiveness of a collision, and that is something called orientation. Orientation is how the two pieces hit each other. Do they hit in just the right way? Do they come together in just the right way to work? And the best way to think about this is this. So when you look at this little picture here, you could imagine that green piece, if we just sort of slid it a little bit over and down in this orientation, right, it would sit in there perfectly. However, imagine a situation where we tried to force this piece in. We sort of rotated it about 90 degrees that direction. It wouldn't fit in, right? It's not going to fit until you get the correct orientation to make it connect with the other three bits, and then you can have the whole thing work together. So the orientation is going to be vital in terms of making sure you can give it all the energy you want. It's just like you forcing the puzzle piece down if you rotated it 90 degrees, and it's not going to come together. So you need both the energy and the correct orientation for those reactants as they come together in order to have an effective collision. Now, let's just sort of roll this together into one thing. And I'm just going to do, I guess, Roman numeral number 3. So what makes an effective collision? This is sort of a general overview. What should I call this? Hold on. Change my mind. I want to call it summary. So we now understand that we need to have energy, the proper amount of energy, and nice spelling of energy, Chang. Sheesh. And the proper orientation. And if we have the proper energy and the proper orientation, then we can actually have something called an effective collision, so that the two things will come together. And if we have enough effective energy and proper orientation, that's going to have an impact on our rate of reaction, right? Our rate of reaction, because if we can, the more effective collisions we have, the higher our rate of reaction will be. So here's a list of those things that will have an impact on our energy and our orientation, and therefore have an impact on the overall rate. So this is 6 things that are going to impact our rate of reaction. Actually, I lied to you. I'm going to stop right here because this has already gone long enough. So I'm going to go backwards to here. We will talk about this in the next screencast. Bye.